Chemical Engineering 757, Polymeric Rheology, H. Winter, Lecture 20A. The rheological behavior of polymeric systems gets real interesting when we go to large strains. We push the material away from its equilibrium structure, and then we have to probe it and characterize it at those out of equilibrium conditions. The question becomes, is then the following. Which constitutive equation can we use for the behavior at large strains? At small strains, we know one equation is good enough. It's the Boltzmann equation, and we can use that for shear extension for any flow at small strains. But at large strains, it is quite difficult to formulate constitutive equations. And I want to start discussing this subject today and also in the following lecture. Continuum mechanics gives us some guidance in formulating those constitutive equations. So we are looking for an equation which is easy to use, looking for equation for the stress, which is easy to use, which describes the rheological behavior accurately, and hopefully has some connection to molecular dynamics so that we would correlate the macroscopic behavior to the molecular behavior in that system. And we are that's really an open subject. So continuum mechanics gives us some guidance. There is the principle of local action, which basically says that the stress in a material element depends on the strain history of that material element and is independent of the strain history of neighboring material elements. And that's the so-called condition for the simple fluid of null. There are other principles. The stress should always relax, or events in the past would always have less and less importance for the stress when they are further and further in the past. And then the equation should be formulated so that a solid state rotation doesn't give any stress contribution, and we know already how to do that. So those conditions come from continuum mechanics. In the following, we will restrict that somewhat further. We will talk about isotropic materials. Those are materials which in equilibrium have properties independent of direction. When you deform an isotropic material, you might introduce some anisotropy, and then when probing the material is not isotropic anymore. But still, a material at rest, which is isotropic, will be described by an isotropic material function, and we will use that in constitutive equations. We will assume that the material is homogeneous. That means that any composition fluctuations are at much smaller length scale than the size of our sample. We treat the material as incompressible, which simplifies the strain measures. We can calculate just things much more easily. And then we also eliminate thermodynamics. We wouldn't include pressure and temperature effects on density. The properties will be held constant throughout the derivations, except for one case where we talk about non-isothermal conditions. And then, of course, the properties, let's say relaxation times, depend on temperature, and we have to introduce that. But for most cases, the properties will be constant. So the behavior is much reduced by introducing those conditions. We will look for the stress now as a function of the strain history. And a constitutive equation, for instance, as a solid could be written as such. Here it would have a isotropic term which contributes to the stress, and then it has a term which is a functional of the strain history. That's the unknown part. That's what we would like to know. And in case of a reference state where the material is stress-free, we can use that stress-free state to define strain tensors. In the case of a solid, there's always a stress-free shape to which the solid material will return when we let go. So we can use that this reference state. If you formulate a constitutive equation for a liquid, then you don't have a reference shape where the material is stress-free, and you only can use the current shape as reference for defining strain tensors. That's why the strain tensor is always defined between T and T prime. While in the solid cases, the strain tensor is defined between T0 and T. That's an equilibrium contribution. And then for transient contributions, you always can formulate something like in a liquid. That's you're free to do that. For ideal solid, this will not contribute. We only have this type of contribution. We will come back to this. Okay, so this vanishes for the ideal solid. The path to go from T prime to T will not have any influence on the state of the stress in the ideal case of a rubber, which is not lost, which doesn't have any losses associated with the deformation. The starting point for many constitutive equations is really the linear viscoelastic model. That's why we spend so much time on looking at the linear viscoelastic behavior of various materials. The only property which comes in is the relaxation modulus. That's the only material property which you need to describe all linear viscoelastic functions. The relaxation modulus contains the relaxation time spectrum, so somehow time behavior at small strain is covered when you know the Boltzmann equation. So this is our starting condition, the Boltzmann equation with the relaxation modulus, which you could formulate in a discrete fashion or in a continuous fashion. Each of them are pretty much on an equal footing. There's no difference. And previously we were concerned about molecular aspects, molecular effects, which would change this type of equation, which would affect the spectrum. The limitations of that approach are the following. The strain was described by an additivity. Remember, in the derivation of the Boltzmann equation, we added the effect of consecutive strains to get the stress response in those cases. At large strains, the strains are not additive, so we have to do something about that. So we have to modify the strain tensors to accommodate for this. In case of differential models, which we haven't discussed much, the time derivatives are plain partial derivatives at small strains, but you have to go to the co-rotational derivatives, Zaremba, Fromm, and those people last century, or in 1950, Oldroyd derived time derivatives to accommodate large deformations in a co-deforming coordinate system. So we would have to accommodate for that if we go to larger strains. And secondly, the material is in equilibrium, in an equilibrium state when we talk about Boltzmann equation, and we would have to accommodate out of equilibrium phenomena in our modification of the constitutive equations. So in all cases, will we have the large strain model reducing to the linear viscoelastic model when we go to small strains. That limiting behavior always has to be conserved. Let's therefore look at other formats of the Boltzmann equation. Here is a Boltzmann equation with a memory function. This is the time derivative of the modulus, and it's formulated here with a strain. Before we had the relaxation modulus and strain rate. So that's a very common formulation, and the memory function again can be formulated in discrete and continuous form. We also can represent the Boltzmann equation as a set of differential equations. Here the stress is given by individual stress components, and each component would be a Maxwell mode if we have this type of equation. That's really our choice. And this time derivative is still the small strain derivative. We would have to modify this to put in an Oldroyd derivative, and then you already have a constitutive equation, which in the first order is suitable for large deformations. Let me stress this small strain limit a little further. Many constitutive equations have been proposed which don't reduce to the linear viscoelastic model at small strains. And we don't want to lose all the information which we already have about linear viscoelasticity. We want to build on that information. Therefore, the experiments tell us that at smaller and smaller strains, any constitutive equation should, if it describes the experimental behavior, should reduce to the linear viscoelastic limit, and that eliminates many, many constitutive equations. There are especially constitutive equations for which the strain rate is used to modify the relaxation modulus and the relaxation spectrum. So whenever the strain rate is used, which was by intuition one way of looking at shear thinning. So if the strain rate is used to modify the relaxation spectrum to obtain a constitutive equation for large strain, then you're losing the ability to, that in the limit of small strains, you go to the linear viscoelastic limit. Because linear viscoelasticity can be performed at very high rates. You can perform a dynamic mechanical experiment at very high frequency. And at this high frequency, it still should reduce to the linear viscoelastic model. But if you have the strain rate in your constitutive equation, the model always blows up or deteriorates in this type of experiment. So all constitutive equations which contain the strain rate to modify the spectrum will not be discussed further in this class because they are useless. You just add, you get more problems than you're solving when doing that. This has been discussed in major detail by Marucci and Astarita in Rheological Acta in 74. So that's a nice article to catch up on that perspective. So how do we proceed to obtain a constitutive equation? There are two major routes to go. One is the experimental route, where we just measure a set of material functions in shear and extension with different transient behavior, different time behavior, and look for systematic patterns in those data. And then we modify the Boltzmann equation, or it's really up to you, define a constitutive equation from scratch, which would mimic the observed patterns. And then you you mimic that, and then you have a proposal for a rheological constitutive equation, which you then can test against other experimental results and see where it fails, where it succeeds, and then you modify that, modify your equation. You put your name then on this equation and try to advertise it so that everybody is going to use your equation. There's another approach, the molecular dynamics approach, where a molecular model is put forward. And for this molecular model, or the model for the molecular motion, you would write down a force balance. We will have a lecture on that subject from Mutu coming up. So you write the force balance, then come up with a constitutive equation. And again, this constitutive equation can be tested against experiments. And if it works out, then you're happy, and everybody else will try to find a counterexample to destroy your proposed equation and come up with a new model. So there's a big difference in linear viscoelasticity and small strain. We have just one equation, and that's good for shear extension for all experiments. But at large strains, the market is wide open. You can propose things quite wildly. The phenomena which you would like to describe would be strain thinning. That would be a thinning in shear and also an extension of flow. Somehow the structure breaks down. You would like to capture that in your equation. And then you would like to describe large recovery of the material. Say a polymer melt being deformed has the ability to retract to its stress-free state if you just put on a short load and then go back. Pioneering experiments have been done in the early 70s by Meissner and later by Laun at BASF, and then also by Osaki and his group in Japan. Let me start with Osaki's experiment in step strain. He took a polymer solution, 20% polystyrene solution, deformed that solution in a step strain and held the strain constant shape, and he built up a stress and looked at the relaxation. The relaxation as a function of time was always the same as long as he stayed at small strains, but then when the strain increased, it went down like this. But Osaki realized that he could shift those curves. Since they have all the shape, he just shift them upward, and he could describe everything in a single master curve where the relaxation modulus as function of time and strain is given by the time dependence at small strain. See, that's where linear viscoelasticity comes in, multiplied with the strain dependence. And that this result, which has found wide recognition early on, has changed or has influenced the search for constitutive equations considerably. We are calling this the factorization, describing a strain and time dependence in a set of two individual functions. It has the advantage that we know already the time dependence because we can measure that in linear viscoelasticity. So we are already halfway towards a good constitutive equation. We only would have to know the strain dependence. This is obviously a very simple experiment, so the factorization might hold in this case. It might not hold in other cases, and that has to be tested further. But it seems to hold, and constitutive equations of Dorian-Edwards, for instance, are based on the factorization based on the separation of strain and time dependence. So key result in 1971. The small deviations here at short times are there because of the glassy behavior at very, very short times, or maybe startup problems. It's a polymer solution, so you have to look at very, very short times to see the glassy behavior. Everything is measured at room temperature at 33.5 degrees in Osaki's lab. On polyethylene melts, the same behavior has been found. Laun described that very nicely. This is a very comprehensive article, very, very good reading, in 1978, where he subjected a material to small strains and then increasing strain levels, and he finds exactly the same behavior as Osaki did. Here, this is the article of Laun, where you can find those results nicely reviewed. It's a quite comprehensive characterization of a characteristic polymer melt. Laun gives also data about the startup of shear flow. So far we only looked at step strain in the moment. Now what happens if we turn on the rheometer? Rheometer is filled with our sample. The shear rate is put to some constant value, and it's kept, so the material really keeps being sheared, and the stress response is measured. The shear stress will increase, and at very low rates it would keep increasing, but at higher rates it goes to a maximum and then levels off. That's so-called overshoot. The real data shown here on a log scale, the time is given in a log scale. The time actually has been multiplied with a constant shear rate, so we are looking at the total strain introduced in the sample, strain of 1, 10, and 100 in that steady shear experiment. Plotted is the response. The shear stress, for instance, goes through a maximum and then levels off. Maximum is not as visible, but when it's being stretched out in the log scale, it's much more dramatic when you see it in real scale. And the first normal stress difference is also going through a maximum, and then it's decaying. These experiments have been performed at different stress levels, and they're normalized. You can see that the maximum for the shear stress, for the normal stress difference, occurs at twice the strain as the maximum of the shear stress. And this occurs at all stress levels. And that's an interesting observation. Somehow the structure breaks down as a function of strain, independent whether you do it at large stress levels or at low stress levels. And that's also an interesting observation which helped formulating constitutive equation. Again, the strain comes in as a measure for modifying constitutive equations. In addition to stress and normal stress difference, Lown also plotted the recoverable shear. That's the shear which occurs like this. You're deforming a material for a certain time, and then you take off the stress, and then the material bounces back. And you measure how much does it bounce back. So we're plotting the total strain here, introduced in the sample, versus the strain of bouncing back. And this is a linear measure here. Look at this. At a strain of 1, introduced strain of 1, when you let go, the recovery is nearly total. If you introduce a strain of 10, then you recover a strain of about 3. And that's the maximum possible strain. If you shear further, the structure breaks down, and the recovery is not as strong anymore. So you can really argue already in terms of, or I'm already talking about structural breakdown because of lack of elasticity in this case. And so this also goes through a maximum. The high elasticity is a typical fingerprint of the material. Meissner performed classical experiments on a polyethylene melt where the shear stress as a function of time has been plotted for high stress levels and for low stress levels or for low rates. Now the shear stress was normalized with the rate. That's why the low rate data are close to the linear viscoelastic limit, and high rates give lots of shear thinning. This is done in a log-log scale because the shear thinning phenomenon decreases the stress level or the viscosity by 1 or 2 or sometimes 3 orders of magnitude. So it's a very large phenomenon, the shear thinning. And here's the first normal stress coefficient, tau 1, 1 minus tau 2, 2 over the shear rate square. And so this is the coefficient of the first normal stress difference. And you can see already the linear viscoelastic limit and then breaking down in some overshoots. Very helpful to have those data. The maxima of, in those experiments, this is the maximum value for the first normal stress coefficient, the shear stress, are very high at low strain levels. There's a linear viscoelastic limit somehow, and then they go down. And this is an expression of shear thinning, which affects the shear stress as well as the elasticity as the first normal stress difference. Meissner also performed experiments in uniaxial extension. He took a rod-like sample and pulled it at constant extension rates. We talked about his device already when we talked about rheometers. So he pulled and he measured the normal stress on the surfaces to stretch the fiber. And this normal stress on this face minus the normal stress on the side face gives us the first normal stress difference divided by the extension rate. He performed an experiment where he had the whole sample at rest, and then he started up at constant rate, measured the resulting stress, and you can see that the stress increases for a while. This lower curve is the linear viscoelastic limit. This is the curve you would get in startup of extension of flow at very low rates, the linear viscoelastic limit. But when you go to higher rates, at some time the stress increases and it starts to blow up. So somehow strain hardening or something is happening. Turns out that it is fairly simple to model this phenomenon when following Lodge's approach, when following Lodge's rubber-like liquid. We will discuss his approach. So you will be surprised how well this behavior is modeled by a constitutive equation with a reasonable strain. Yeah. Yes, right. The units are Pascal seconds. Yeah, please note this. Yeah, thank you. So it's Pascal seconds. So viscosity. Yeah. The behavior of polymer melts is somewhat similar to the behavior of rubber. The large recovery, all those elastic phenomena, and the appearance of a polymer melt at intermediate time scales in the rubbery plateau is so close to rubber that we should look at rubber behavior for a moment. I won't discuss it in great detail, but we should look at it somewhat because it gave guidance in the formulation of constitutive equations. So let's look at an ideal elastic solid in the moment. That's the solid which doesn't have any lossy contribution. Its stress is fully determined by the strain between the instantaneous state and the stress-free state. So only the deformation from the stress-free state to the current state is needed. This is one of those extra pages which were left out initially. Now the T0 denotes the stress-free state, and important to note, the path which you use to go from the stress-free state to T is without any influence on the stress. You can do it fast or slowly or with any deviations. It has no influence. And that's where the ideal behavior comes in. We are neglecting all losses in our system. I will come back to this in a moment. So let's take this ideal behavior and write the most general form of a constitutive equation which describes this type of behavior. And this has been proposed by Finger. So this is Finger's solid, we could call it. And that's why also the strain tensor is called Finger tensor, and this is the Cauchy tensor. So Finger said that the stress is given by an isotropic contribution plus the contribution of the Finger strain tensor between the stress-free state and the current state multiplied with some modulus plus the contribution of the Cauchy tensor between T0 and T. I should put in a 0 here, between T0 and T. The Cauchy tensor at small strain reduces to something negative. That's why we pulled the negative sign outside so that we have a positive property here. The parameters used are the Cauchy strain tensor, Finger strain tensor between the stress-free and the current state, and we have two moduli which might depend on the strain invariance. If we have a material of constant density, then the third invariant is equal to 1 and has no effect. So we only would deal with the influence of this first and second invariant. So those will appear in our constitutive equation. The molecular theory for rubber, which has been derived by Treloar, only gives a modulus G1, and this we would call the Young's modulus in this case. And there would be no contribution G2. So from a molecular point of view, G2 is equal to 0, but experiments tell us that there's a finite contribution that we should leave that in there. So in the moment, I just carry this and look at the consequences. Now, which material would be modeled by that? We would look at a network polymer away from TG, so it would be in the rubbery state. And it would be a material which, at small strain, has a linear relaxation modulus given by an equilibrium contribution and a transient contribution. Now, this transient contribution would be equal to 0 because that would give us a contribution of the path. So the ideal rubber has G of T without any time dependence being just a constant value. And I brought a sample here for you. I have two rubber spheres here. I want to show you those spheres. Two rubber spheres, and they behave slightly different. They have different molecular structure. And one of them, if I let it bounce here, if it's ideal rubber, then the bounce should be as high as its initial position. You can see that when I have it bouncing once, it doesn't go up completely. So there's some loss in this rubber already. And here's another material which is far away from ideal behavior. It's also a piece of rubber. If I let it drop, it just stays down there. All the energy, the static energy, is converted into kinetic energy, and upon hitting, it's converted into internal energy, into heat. So it's a material which is very lossy, but it is it's also rubber. So when you touch it, both are very, very similar in their behavior. When you roll them, you can see that one has a much higher resistance. The lossy part, the lossy rubber has a higher resistance against rolling, because when deforming, all the energy which you put in there cannot be recovered. It's lost. So you can see that the bouncy ball is going much further. Now the bouncy ball actually is, you can buy those in toy stores, and this is the happy ball, and this is the unhappy ball. So we are talking about the happy, the rubber of the happy ball. If you want to talk about this other rubber, you would have to include a viscous contribution. Here, this contribution. We can do that because we will talk about liquids very soon. And when talking about liquids, we have to formulate something about this lossy part. So when combining the liquid behavior with the ideal rubber, you will be able to model the unhappy rubber ball behavior. By the way, this lossy rubber is used in the fast trains for damping materials, and also used in racing car tires, because you need lots of friction on the surface, and probably don't worry about the losses, since the engine is strong enough to overcome that, as long as if you don't slide off the road. So this increased friction is an advantage. Let's come back to the ideal solid behavior. The finger solid here, the behavior of that material in axisymmetric extension, where the material is subjected to a strain or a stretch, which is given by L, instantaneous L over initial L. So the stress in that material is given as an isotropic contribution plus the finger strain contribution minus the Cauchy strain contribution. And in this case, I already subtracted one on each, subtracted the unit tensor to make it more simple. The first normal stress difference, which we are interested in uniaxial extension, is given by the difference between those two components. We just add up those terms, and we find that it's equal to G1 plus G2 over L times L squared minus 1 over L. Pi 2 is equal to pi 3 due to the symmetry of the stretching experiment. In shear now, where a shear strain is introduced of that format, we can calculate the shear stress by taking the 1-2 components here for the stress. No contribution here. Have G1 gamma plus G2 gamma. So G1 plus G2 are adding up in gamma. And we cannot distinguish between individual components. So here we wouldn't care whether we have everything formulated with a finger strain or Cauchy strain. Similarly, the first normal stress difference, where on the diagonal here, pi 1 minus pi 2 is taken, and the difference between this one, G1 times gamma squared minus 0, plus G2 times 0 minus this, and the two minuses cancel. So we have gamma squared in both cases. So we have G1 plus G2 times gamma squared, and that gives us the first normal stress difference. For the second normal stress difference, we only have a contribution if the Cauchy strain tensor has a finite factor in front. So if G2 is finite, and it is certainly minus, it's negative, so the minus sign is okay. That's what we would expect in the system. And G2 probably has a finite value. Yes?
Should there be ones on the diagonal for those Cauchy tensors, finger strain tensors?
Should be where? On the
Diagonal, where there isn't the gamma, on the shear.
Oh no, for the shear we only have an off-diagonal term. We have not if we subtract one. I subtracted a unit tensor like here. I took the question is whether there should be gamma squared plus 1, 1, 1, and you have 1, and then minus 1 minus gamma squared and 1. You can formulate it with that, in that formalism also, and it will not give a different result because you take the difference here between pi 1, the 1, 1, and the 2, 2 component, and then this is dropping out. It's an isotropic contribution which you would be getting. Yes, yes, would alter the P of T term. We neglect the compressibility of the material, and then the pressure is not a thermodynamic variable. So P just contains an isotropic contribution, and we can add or subtract things freely to that. It wouldn't contribute to the stress. The stretching of a rubber band has been modeled by Mooney in 1940, and he found that the Hookean behavior, which would be given like with a straight line here, is not adequate. The equation which we just calculated using Finger's formalism of the last century is more appropriate, and that gives the curvature in a somewhat better fashion. So this is a rubber band in extension. How about a rubber cylinder, a rubber band now in torsion? We have a little cylinder, and we are twisting it at the ends. When doing this and leaving the ends free, it will will decrease its size in the middle, and it will bulge out here at the ends. Now, if you apply a stress on the ends, if a pressure profile at the ends to make the surface flat, then the necking disappears. You restore the old shape, but you need a pressure. Those are so-called normal stress effects, which we also see in polymeric liquids. There's a great similarity in this rubber behavior and the behavior of polymeric liquids. In vacuum molding, you could use equations like that. If you, for instance, make a cup like this here, you would have a sheet which you clamp in a device, and then you punch it from one side, or you simply apply a pressure difference, a higher pressure on this side than on the other side, and then you blow it like kids blow a piece of chewing gum. So that chewing gum experiment is described here in vacuum molding, where a sheet is held by some clamping, pressure difference is applied, it starts curving, and eventually it will touch the mold, and you will get the final shape. The stretching, the equibiaxial extension, is given by the final h or instantaneous h divided by its initial h, and that is decreasing in time, h. The wall is getting thinner as you stretch it, so this is a smaller one. Otherwise, it's the same deformation as uniaxial extension, but it has a reverse, it has a negative stretching rate in that sense. You again will have the same equation for the stress as we formulated before. Pi 2, 2 is the stress within the plane. 2, 2 and 3, 3 are in the plane. 1, 1 is coming normal to the surface. So this is the tension in the skin, and pi 1, 1 is given by the air pressure. Turns out the air pressure is pretty much the same on both sides. You don't need very high pressures. So it is close to minus pi 0. And now pi 2, 2 we know is a tension. The question is this positive? And you can see that this is positive because this term here will be negative if L is smaller 1, then this will be negative, and we have minus pi 2, 2 equal to a negative term. So this is pi 2, 2 is positive, and is a tension in the skin, which we then can introduce in an equation down here, where the pressure difference is given by the radius of curvature, and the height of that skin is just a thin skin model, and it's given also by the tension in that skin, and that's the tension which we just described up here. So with Finger's equation, you can model stresses in liquids like that. There is a strain energy approach which has been used quite extensively. The principal stress components in a little material element can be written by a stress tensor like this. Actually, we are saying the material is stress-free. We are applying a small stress to that material, and when describing the stress, we pick a coordinate system which is coaxial with the stress ellipsoid. So without losing any generality, we just use a principal coordinate system, pick an infinitesimal material element, and on the faces of this material element, we only will have normal stresses, no shear stresses being applied due to that simple choice of coordinate system. The work which results from that deformation from L1 to L1 plus delta L1, L2 goes into L2 plus delta L2, and 3 goes into that new strain. They can be positive or negative. So the work used for generating this deformation divided by the volume of our little cube is the so-called strain energy function, and the increment is given by the force in one direction times the displacement in one direction, plus the force in two direction times the displacement in two direction, plus the 3 component, and the whole thing is divided by the volume of our little cube. Now, the force is given by the normal stress multiplied with the area of that cube. So we have on the one face pi 1, 1 acting, multiplied with the area, L2 times L3, times the displacement. And we do this with a 2 surface and a 3 surface, divide by the volume, and find that delta V now is given by the stress component, normal stress in one direction, plus the strain, dL1 divided by L1. This is the Henke strain, epsilon 1. And the same, or the equivalent contribution we get on the 2 surface, where we have a normal stress, pi 2, 2, and a strain, epsilon 2, and on the 3 phase, pi 3, 3 times epsilon 3. In the meantime, I moved from a finite strain to a small strain so that we can rewrite everything in a differential formalism. And we find that the stress components are really defined by the energy per unit volume, which we use by the strain energy function. So the derivative of the strain energy function with respect to displacement in I direction multiplied with the length in I direction give us the 1, component of the stress. We can do this with all 3 components and introduce that back into the constitutive equation. And Finger's equation now looks somewhat different. We have an expression now for the first modulus and for the second modulus. And you can, when going through all the derivations, you can show that the derivative of the strain energy function with respect to the finger strain tensor multiplied with the finger strain component is giving us the first term. And the derivative of the strain energy function with respect to the first invariant of the Cauchy tensor gives us the second modulus, and we multiply that with the Cauchy strain component. So we have an expression now for G1 and G2. Let's take a short break here and then go to the liquid behavior and see how those concepts can be expanded to look at polymeric liquids. University of Massachusetts at Amherst, Chemical Engineering, Polymer Science 757, Polymer Rheology, H.H. Winter, Lecture 20B. We discussed 2 concepts. One was the linear viscoelastic model, and the other one the constitutive equation for a rubbery material. Let's see how we can combine those concepts in a phenomenological approach to understand polymer melts and polymer solutions, polymeric liquids in general. The history of this development goes back to the 40s and 50s and so on. James and Green and Tobolsky, Yamamoto and Lodge. In 1954, Lodge wrote his book Elastic Liquids, and that's a a milestone in the development of those constitutive equations. It has had a large impact in the development of constitutive equations. So the most general constitutive equations, which only has a single integral, you can go to multiple integral formulations, very complicated formulations. So the most simple model is the one proposed by K, and also by those people here, but recently K, Bernstein, Kirsley, and Zappas, and by Rivlin and Sawyers, and it goes something like this. You have the stress given by an isotropic contribution plus a contribution of the finger strain tensor plus a contribution of the Cauchy strain tensors, and since this is negative, we would have a minus sign here. I want to point this out. This is important. Or you change order here, 1 minus Cauchy tensor, and then this would be plus. Two material functions are needed, the memory functions, which depend on time somehow now, and they depend on the invariance. The third invariant will drop out for incompressible materials. In the limit of small strain, where the Cauchy tensor reduces to the unit tensor, and also the finger tensor reduces to the unit tensor, M1 and M2 reduce to the memory function of the linear viscoelastic material. So this would be just the time derivative of the relaxation modulus, and that's equal to the time derivative of the spectrum here as formulated. So we should keep in mind that this equation has a well-defined limit at small strains given by linear viscoelasticity. Lodge used he modified the rubber theory of Treloar to describe a system which doesn't have permanent network junctions, but physical junctions which have a finite lifetime. And for those, he found elastic behavior on short time scales and viscous behavior and long time scales. And this intermediate behavior is given here. The stress is given by isotropic contribution plus the memory function times the finger strain tensor, and he doesn't have the Cauchy contribution here. There's only one material function, which is the memory function, and that's given by the time derivative of the relaxation modulus. In the case of the large model, the material structure is in equilibrium at all times, and therefore the relaxation spectrum of linear viscoelasticity can be used to describe the memory function completely. So we're talking about large strain behavior or finite strain behavior in a material which has still equilibrium properties from a molecular point of view. So it's an intermediate model which we are going to discuss. And at those intermediate strains, up to maybe shear strains of 2 or 3, it gives predictions which agree very nicely with experiments. Also in extension, up to extensional strains of 3, it agrees very nicely with experiments. If you go to larger strains, then you have strain thinning coming in, and somehow you're moving away from equilibrium. I want to go through a few exercises to show the capabilities of that model. Now, in those exercises, we will include M1 and M2. So I'm not really staying strictly to largest rubber-like liquid model. And we will look at the stress in shear. Now, the stress components in shear are formulated in a certain coordinate system. It's a plane stress, so there are zeros over here. We only have one shear stress and two normal stress differences, which we have to describe in that coordinate system in shear flow. This is the contribution of the finger strain tensor. This is the contribution of the Cauchy strain tensor. You can leave the ones in or take them out. It doesn't make any difference in the calculations. In extension, we use a principal coordinate system, so we only have two normal stress differences, first and second normal stress difference, given by the finger strain component and the Cauchy strain component. The first experiment to look at would be a step strain. we are deforming the material in the way Osaki did it in his initial experiments. He did a shear experiment, but here we are looking also at shear. So the stress is given by shear. This is the strain tensor. It only has a contribution from minus infinity to the current time t. There's no further strain between 0 and t. So the second part of the integral this integral goes from minus infinity to current time t. So this the contribution from t prime equals 0 to t prime equal t is eliminated, doesn't contribute. And here we put in the step strain for the Cauchy tensor, the step strain for the finger tensor. Here you see the minus sign coming in, and that cancels with this minus sign. And the shear stress calculated from this is equal to the following. Tau 1, 2 is equal to this integral times m1 times gamma 0. Minus and minus cancel, so we have plus m2 times gamma 0. Gamma 0 is put outside, and we have m1 plus m2 integrated, and that's certainly the modulus of linear viscoelasticity, so our response is as expected. It actually is the linear viscoelastic response in which we are calculating, which we are predicting, and this is the intermediate state we are looking at. The first normal stress difference can also be calculated. Tau 11 minus tau 22 is equal to m1 times gamma 0 squared minus m2 times 0 minus gamma 0 squared. This minus, the two minuses drop out. So for the first normal stress difference, we have m1 plus m2, and gamma 0 is outside because it's constant, and we have the expected result gamma 0 squared times g of t. The relaxation of the stress, of the shear stress, goes with the same time function as the first normal stress difference. So when you take a ratio, I did this down here. No, I just formulated it. The shear stress divided by the shear strain equals first normal stress difference divided by the square of the shear strain is equal to g of t. And this is the so-called Lodge-Meissner relation, saying that the normal stress and shear stress relax in the same fashion. When looking at the second normal stress difference, tau 22 minus tau 33, you see that the finger strain doesn't contribute, only the Cauchy tensor contributes. It comes in with a minus sign here, minus gamma 0 times this integral, and this would be the 2 contribution if we split up our relaxation modulus in a 1 contribution and 2 contribution, and this would be not the total modulus, but only the Cauchy contribution. And it has a minus sign here, which is in agreement with experimental observation. It's always negative, this second normal stress difference in polymeric melts, in isotropic polymer melts in polymer solution. So the sign is okay, but we don't know the contribution there. Now, you can do the same thing in uniaxial extension. We describe the stress in the 2 contribution, finger strain, Cauchy strain tensor. Again, the minus sign is coming in. You can see now that this finger strain contribution and step strain is constant, can be put outside, and our integral now goes from minus infinity to 0, because in that range it's constant. In the other part it's 0, plus the contribution from the Cauchy tensor, which comes in with a negative sign. We put this Cauchy tensor outside and have this contribution. We put in the components for the finger strain tensor and uniaxial extension, and the components for the Cauchy strain tensor in uniaxial extension. All of those we did in the initial part of the class, lecture 3 or so. And from that we calculate the first normal stress difference divided by the strain. Now the strain is coming in with L0 squared minus L0 minus 1. L0 is the step strain, the stretching which we put into the sample. And that has a contribution from the finger strain tensor and from the Cauchy strain tensor. Therefore, you can see that the 2 contribution have a different, have independent weight when calculating or when describing this type of experiment. And we really should know how big those components are. There's not much information available on those things. It's very hard to perform a step strain experiment in extension. We can generalize this approach. We don't really have to talk about uniaxial extension or uniaxial or simple shear. We can just say we're putting in a step strain defined by a Cauchy tensor or the equivalent finger strain tensor. So in the general formalism is something like this. We put in a strain tensor. Here is a tensor we are plotting, and it has 9 components. I didn't specify that, so just assume it's 0 here, and it's a 0 tensor here, and it's a constant tensor over here. The stress response relaxes. The specific strain tensor is given in those 2 ranges like this. And we are changing now the integral from -infinity to t as given here, actually using only the finger strain contribution. We put this outside and then obtain the same Lodge-Meissner relation for general formalism. You can really generalize that. You can say that the stress is given by a constant times the relaxation modulus. In all stress components, independent whether this is shear or extension or whichever component you're looking at, they are decaying with the same time function. And that's pretty close for what's being observed in experiments. Another experiment which is interesting to look at is startup of shear flow. We put a material in the rheometer and turn the machine on. So the strain rate is 0, and it's finite, it's constant at some time bigger than 0. We are interested in the shear stress response, in the first normal stress response, and also the second normal stress response, and see what's happening in the system. The strain is calculated between times t prime and current time t. Now, if t prime is somewhere in the past, we have the total strain coming in, but the material is being sheared from time 0 to a finite time t. So the total strain is shear rate times the total time t. If we are out here, and if t prime is taken in here, it's the shear rate times the lapse time t minus t prime. Those have to be introduced to obtain the shear stress and the first normal stress difference, and also the second normal stress in these previous equations. I brought a sample of how to do that, just for your. I don't think I made a copy, but you can see the procedure immediately. Those are the stress components, isotropic contribution. This is the first part of the integral from -infinity to 0, having the finger strain tensor here, and then the contribution from -infinity to 0, having the Cauchy strain tensor contribution in here. And here we have then the second part of the integral from 0 to t, and the strain is given by gamma dot 0 times the lapse time t minus t prime. Here this is strain squared. This is just the strain, and all of this. Okay. I think we have to put in a minus sign here to be correct. Okay. So this is the type of calculations you would be doing. And the material functions you will end up with, the material functions to describe the shear stress are given by linear viscoelasticity, by the relaxation modulus, and S times the relaxation modulus integrated from 0 to t. Now, those integrals can be determined analytically if you describe the spectrum with a set of Maxwell modes. This is a discrete spectrum. Or if you have here for the second term, here for the S times the relaxation modulus, here you have just relaxation modulus indicated, S times the relaxation modulus, which occurs in the first normal stress difference. For that, you also have an analytical solution. That's one reason why those discrete spectra are so favored by many people get nice analytical solutions. You can see that we use equilibrium properties. There's no deviation in the moment, no large strain behavior incorporated in all of that. So what's the steady shear behavior of that system? What's the long-term behavior when the startup is over? The viscosity is given by this integral from 0 to infinity. First normal stress difference is given as before, but integral from 0 to infinity, and the second normal stress coefficient can be calculated similarly. But here we have the two component, and we don't know exactly what this is. Now, this is a constant. This is independent of shear rate. So in our picture, we will get the viscosity at low shear rates, the upper limit, and we will get the first normal stress coefficient also at the limit of 0 shear rates. We are talking about the equilibrium part of the experimental spectrum, not the large strain behavior, really. But it's interesting now that with this model, we not only get a viscosity, we also obtain something about some information about elasticity, and that's new. If you describe the behavior with the rate of deformation tensor, then there is no diagonal term. You don't get any normal stress differences. So by using a proper strain tensor, we are able to model the first normal stress difference, model this contribution, and even that contribution if we're able to distinguish between all of that. You can calculate these with the continuous spectra, and you can with the discrete spectra, and you also can calculate those with continuous relaxation time spectra. Just reminder about linear viscoelasticity. You remember that the relaxation modulus is given by a discrete spectrum. You interchange the order of integration, and you find the viscosity is given by the relaxation time spectrum integrated from 0 to infinity. And the first normal stress difference, that's new now. This is a new contribution. It's given by 2 times the integral over g times s ds. You replace gs with a spectrum. You integrate this and find that this is lambda squared, which cancels partially with this lambda. And the first normal stress difference is given by 2 times this integral of the spectrum times lambda d lambda. We can push that example even further. We can describe the material behavior now by the spectrum for monodispersed polymeric material. We know what the spectrum h of lambda is for monodispersed linear flexible polymer. It's given by a power law spectrum like this. So log h of lambda is just a straight line, and it's cut off at lambda max. This h of lambda now is introduced to get the viscosity, the 0 shear viscosity of a monodispersed linear flexible polymer, and that's calculated as n over n plus 1 times the modulus times the longest relaxation time. And now, to expand our knowledge, we can calculate the first normal stress coefficient for steady shear flow for this monodispersed polymer, and this is given by twice this spectrum, and we integrate this as 2n over n plus 2 times the plateau modulus times lambda max square. So we have an analytical solution for the elastic contribution for the monodispersed polymeric material. Another interesting experiment which stimulated the development of rheology significantly is the uniaxial extension, and especially the data measured by Meissner while he was still in industry at the BASF. He took a rod-like sample, equilibrated that sample so that the molecules are relaxed, coiled in equilibrium state, and he stretched them. The measure of stretch would be the instantaneous length divided by some previous length at time t prime, and the stretch between t prime and t is given here as an integral over the extension rate. The resulting stress, which we calculate now using the most general equation for viscoelastic material, staying, I would say, most general if you stay with a single integral and if you stay with linear viscoelastic properties. So the stress is given by the diagonal terms. We're choosing a principal coordinate system. Have the finger strain components and the Cauchy strain components. See, I didn't subtract one here. You can do this in your exercises just freely because we are interested in the normal stress differences, tau 1 minus tau 2, have the finger strain contribution and the Cauchy strain contribution coming in with a minus sign. The specific kinematics we are going to look at is the following. The system is at rest, and then an extension rate at constant value is put onto our sample. We are interested in the stress response. The stress grows, and then somehow it increases if you remember the experimental data. So that was the experimental finding, that at some finite time or finite strain, there's a breaking and the stress increases. The total strain is given by a growth like this, exponential growth. That would be this would be the length change of our sample in an experiment at constant extension rate. The stretch is again described in two time zones. The time zone at rest has a contribution, and the time zone while the experiment is going has also contribution. And we will split our integral to describe those two contributions. The integral is having, the general formulation is this up here. That's the same as in the Mooney equation for the rubber, but here we have now memory functions introduced. So the strain is given in those two time zones. We have the first integral from minus infinity to 0, having the finger strain and the Cauchy strain contribution, and a second integral from 0 to t, and again having the finger strain and the Cauchy strain contribution. The first contribution here, or the first part can be integrated. Here, this is an integration for over t prime. All of this can be put outside since it's constant. And specifically then when looking at this part of the integral, this exponential function will also go outside. So the first part of the integral we can formulate very easily. We can replace the memory function with differentials of the relaxation modulus, the first part and the second part. And we can formulate now the second integral from 0 to t. And again, we replace the memory function with the derivative of the moduli, the finger strain modulus and the Cauchy strain modulus. This integrates now further in the first part very easily. We don't have to specify. We just integrate. We had the time derivative of the first modulus and the second modulus. And when you integrate this, you get the moduli themselves. That's why we introduced that. But for the second part, the integral is too complicated, and we have to specify the relaxation behavior. In this case, I picked a relaxation modulus given by Maxwell modes. And the first one, I put in a weight function, 1 minus alpha. And alpha would be very small. And the second contribution going with the Cauchy strain tensor having alpha. So the sum of the two would eliminate this, and G1 plus G2 would be the relaxation modulus, which we use in linear viscoelasticity, just to make sure that we are satisfying the limiting behavior at very, very small strain. Note that in this calculation, these terms occur. 1 minus 2 epsilon dot times lambda I, and lambda i's are now the individual relaxation modes for the model. And here 1 minus epsilon dot lambda I. If we choose a large extension rate, and we are free to choose any large extension rate in our experiment, right? That's our experimental parameter. So we can choose this large enough so that the total product, which is dimensionless, is bigger than 1. And then this group is negative. Okay? This is negative. This group also occurs up here, and it also will become negative, canceling the negative sign up front, and you have an exponential function which contains t, and it has a positive exponent. So this function will blow up. And this term here is the reason for the blowing up of the stresses in the startup of uniaxial extension of flow. There's the longest relaxation time, which will blow up first, and the contribution of the shorter and shorter relaxation times will follow at higher extension rates. And this is why this, depending on the choice of extension rates, well, it always will pick the longest relaxation time, really, to diverge. And this is shown in Meissner's data. When you look at his data, at the highest extension rate, the stress is increasing normally, and then it will diverge at a certain value where the time is large enough. So you see those fast diverging time functions or more slowly diverging time functions. And if the extension rate is really very, very low, then it doesn't diverge, and it's all acting quite normal. So that was a tremendous success of Lodge's rubber-like liquid theory. He could describe data which Meissner found in, well, Meissner did those experiments afterwards, but the two of them got together, discussed those data, had a tremendous impact on the development of constitutive equations for those viscoelastic liquids. Let me sum up our results which we had today. The predictions of the viscoelastic model, the integral model which we looked at, are very nice for normal stresses, for recoil, and for relaxation, as long as we stayed in fairly small strains. Also, the stress growth in uniaxial extension has been modeled very nicely. That's actually one of the biggest successes. It was quite surprising that you can describe the stress growth experiment now as a simple homework problem. You can just calculate it on the back of an envelope using the large rubber-like liquid and a finger strain tensor, and there you are. So that's a lot of success in a simple model which was derived from rubber elasticity. However, there are limitations. Certainly, the constant viscosity which we are predicting with this model is not in agreement with experiment. We would need shear thinning. Also, the first normal stress coefficient has a structure dependence. It also goes down at large rates. Now the viscosity in a startup experiment would grow and level off at very low rates of deformation in the linear viscoelastic limit, but at higher rates it goes to a maximum and decay. So we have to somehow incorporate that shear thinning phenomenon in a future constitutive equation. You have to modify that equation to accommodate quite this observation. And also we have to go back to Osaki's experiment of increasing strains in a step strain experiment, and also have to explain why relaxation occurs faster at larger strains, but at the same distribution of relaxation times. The whole time spectrum is just shifted down to, everything is shifted to in an equal fashion. Next time we will expand on this concept. We will look at large rubber-like liquid in a little further detail, and also go to large strain behavior, shear thinning behavior, and see how all this fits together.